In this lesson, we will be covering proof by mathematical induction. Here is an example. Before we begin this proof, we need to know what exactly we are trying to prove. On the left-hand side, we have a series of terms that are increasing by 3 as we go along. The first term is 2, the second term is 5, and the third term is 8. Now suppose we want to know the fourth term. We can do one of two things. We could add 3 to 8 and get 11, or we could substitute n equals 4 into the formula 3n minus 1, and we would also get 11. So this formula on the left-hand side is called the nth term formula. So for example, if you want the fifth term, you replace n with 5, and replace n with 6 to get the sixth term, and so on. The formula on the right-hand side gives us the sum of the first n terms. So, for example, if you want to know the sum of the first two terms in the series, you can do one of two things. You can add 2 and 5 to get 7, or you can substitute 2 for n in the formula. You'll get the same 7. Also, if you want the sum of the first three terms, you can add 2, 5, and 8 to get 15. Or you could substitute 3 for n in the summation formula on the right, and you'll also get 15. Our aim is to prove that this formula on the right will always give the correct summation, regardless of the value of n. Proof by induction follows 3 steps. The first step is the base case. This step is all about showing that formula will work for the first term. That's the case where n equals 1. Recall that the formula on the left gives us the nth term. So, substituting n equals 1 in this formula gives us the first term, which we already know is 2. Recall also that the formula on the right gives us the sum of the first n terms. So substituting n equals 1 in this formula should give us the sum of the first term, which should be 2. So the formula works for the case when n equals 1, since the left-hand side and the right-hand side are both equal when n equals 1. The second step is called the induction hypothesis step. In this step, we assume that the formula is true when n equals k, where k is any random natural number. In this step, we simply replace n with k everywhere. The assumption is that if we are adding k number of terms, the n term would be 3k minus 1, while the sum of the first k terms would be k times 3k plus 1 over 2. The third and final step is called the induction step. In this step, we want to prove that the formula is true when n equals k plus 1. Recall that in the step just completed, we assume that the formula works when we have k number of terms. In this step, the aim is to prove that the formula works when we have k plus 1 number of terms, which means that we will add one more term to those that we already have in step 2 on the left. To get this additional term, we can do any one of two things. We already know the terms are increasing by 3, so to get the next term, we can simply add 3 to 3k minus 1, or we can substitute k plus 1 into the nth term formula on the left-hand side above. In both cases, the term at the end will now be 3k plus 2 when simplified. Now let's address the right-hand side. In step 2 above, we replaced n with k because we were summing up k number of terms. In this step, we are summing up k plus 1 number of terms. So now we will have to replace k with k plus 1. So we end up with k plus 1 in the first bracket. In the second bracket, 3 times k is now 3 times k plus 1. We need to multiply both the k and the 1 by 3. So we get 3k plus 3 plus 1 in the second bracket, all over 2. In every induction proof, the equation in step 2 is substituted in step 3. Notice in step 2, the summation from 2 to 3k minus 1 is equal to k times 3k plus 1 over 2. So we can replace the summation of all these terms with k times 3k plus 1 over 2. The objective is now to prove that the left-hand side is equal to the right-hand side. For the terms on the left, let's put everything over a common denominator 2. We can rewrite 3k plus 2 as 3k plus 2 over 1, then multiply numerator and denominator by 2. We can now group all the numerators together, since both fractions now have the same denominator, to show that the left-hand side is equal to the right-hand side. We can either factorize the terms on both sides, or we can expand the brackets and show that both sides are the same. Let's expand the brackets on both sides. On the left, k times 3k plus 1 is 3k square plus k, while 2 times 3k plus 2 is 6k plus 4. Group the like terms, and we get 7k in the middle. On the right, k times 3k is 3k square, k times 4 is 4k, while 1 times 3k is 3k, and 1 times 4 is 4. When the terms are grouped, we get the same thing on both sides. 3k square plus 7k plus 4 all over 2. If we had factorized both sides, we would have had k plus 1 into 3k plus 4 over 2 on both sides. Either way, we have shown that the formula is true for n equals k plus 1. Hence, the formula is true for all values of n, where n is the set of natural numbers, and that completes the proof. In the next video, we will look at how mathematical induction can be used to perform divisibility proofs. See you soon.